Okay, so let's name these aldehydes and ketones. Again, we want to identify the longest chain, giving the carbonyl group right here the lowest possible number. And so in this case, we'll number from the left, 2, 3, 6. So we have hexane, and this is hexanone, ONE to reflect the presence of what's called a ketone, and this is 3-hexanone. And the only other exciting feature on this compound is the 2-methyl group, and so we just write 2-methyl, 3-hexanone, and that's all we have to do. This aldehyde here is going to be a little more exciting, I think. And so the aldehyde will always get carbon number 1. We find that we have octane as our parent compound, and that becomes octanal, Al meaning aldehyde, and we have 3-methyl and 6-methyl, so we have 3,6-dimethyl octanol, and we actually don't need a space between them because there is no number. We don't put 1 octanol because by definition, it being an aldehyde, the aldehyde is at carbon number 1. Then we need some stereochemical designations for 3 and 6. Carbon 3, carbons 4 and 2 are equivalent. Carbon 1 takes priority, then carbon 4, then the methyl group. And so number are going in clockwise. We have 2R. And carbon number 6, carbon 5, it has much more stuff to it versus carbon number 7, and so we would assign highest priority to carbon number 5, then 7, and then this methyl group. And so here we finally see an S stereochemical designation, 6S. So 2R, 6S, dash 3,6-dimethyl octanol. And I can erase that little bit there, turn that into actual octanol, no spaces. Then we're asked to predict the product of the following reaction. So here again is an oxidation reaction. This is a generic oxidizing agent. In this case, I defined it as PCC. As you saw in the video, that's a special type of oxidizing agent that typically deals only with primary alcohols and turns them into aldehydes. So there's our aldehyde. Here again, you saw in the video, ozone can be used to cleave double bonds. And so with DMS workup, we're left behind with 2 ketones. We essentially cleave the double bond. We keep the CC or the C double bond, but now it's a C double bond to O. And we get 2 of them, of course, because we have 2 halves of the alkene. So there's the one, and there's the other. And if you draw it like this, you can see the original structure of the alkene has now just been split in half, and I've added a couple of O's in there to associate with these 2 carbons that have double bonds. The carbons still have double bonds, just not to each other. Okay, this third one has a mixture of compounds, but Na2Cr2O7 is an oxidizing agent that is commonly used in organic chemistry. And in this case, it's going to turn this alcohol into a ketone. And that's all we can do. We can remove these 2 H's, and we're left with a CO double bond where that alcohol used to be. In this case, we will protonate the alkyne, and we're left with a ketone in that spot. So this next one is a biologically relevant reaction. We take an amine and an aldehyde, and we produce a compound called an imine. And so I'll draw it down here. That NH2 bonds twice to the carbon, and we end up with 3 carbons. This N carbon had a double bond, now it has a double bond to the N instead of the O, and the byproduct is water, the two H's plus the O. And that's, again, not that important, but if you draw it, that's fine. If you leave it out, that's fine as well. Up here we have what's called a hydration reaction. We have acid catalyst. We're adding water to this aldehyde. Remember that water is a great nucleophile when we're dealing with carbonyl compounds. And so we end up with this hydrate. We've added water. See, we started with one O attached to this carbon. Now we have two O's and two H's. So we've added essentially water to the CO double bond. In this case, we're using a different nucleophile, an H- nucleophile. So this is a hydride nucleophile. That's what NABH4 does for us. And so what we're going to do is we're going to add that H- to the carbonyl carbon. We end up with an alcohol. Here's the original aldehyde hydrogen, and here's my new hydrogen that I got from my sodium borohydride. So now I have an alcohol where I used to have an aldehyde. So this is a reduction. Here again is a reduction, same conditions, except we are going to reduce a ketone to a secondary alcohol. So here's my new H here. I'll circle it just like I did above. And we have an alcohol produced from this ketone. Here's a primary amine, a ketone, acid catalyst, just like we saw on the bottom left of this page. Instead of a CO double bond, we've now formed a CN double bond. We've lost these two H's, we've lost the O, we've formed water as a byproduct, and we have now an imine. And lastly, we have some acid catalyst. We're adding water to this ketone. And so we end up with the hydrate again. Two O's and two H's now attached to the carbonyl carbon instead of a O with two bonds on it. So looking at these final two reactions, we see an aldehyde that we're asked to react with ethyl magnesium bromide. Remember, that's a Grignard. It's a carbon nucleophile, and it's going to turn our aldehyde into an alcohol, and it's going to add a carbon group equivalent to the ethyl. So here's the ethyl right here, and the original aldehyde hydrogen is right there. And so this is a Grignard reaction here. The last reaction is also a Grignard, where we're asked to add CH3 to a ketone. And so we're going to retain the original ketone carbon structure. We're going to obtain the alcohol, and we're going to add the Grignard CH3 right here as a nucleophile. And so these are both Grignard reactions. We end up with alcohols. In the case of the aldehyde, we end up with a secondary alcohol. In the case of the ketone, we end up with a tertiary alcohol. Now to draw the complete arrow pushing mechanism for the following reactions. Essentially, we're going to draw arrow pushing mechanisms for these Grignard reactions. And so remember that the Grignard looks like this. And so the nucleophile is this CMG bond. It's going to attack the carbonyl. And we end up with this image here. And that's going to be an O- with 3 lone pairs. The original aldehyde hydrogen and our 2 carbon nucleophile, the ethyl group. The second and final step is to have our O- react with the acid in the second step. And so what we're going to do here is simply protonate the O-. That gives us the alcohol that we know is the end product with this Grignard reaction. The second mechanism we're asked to show is a reduction, so a hydride reduction using an H as the nucleophile. And so most time I find it's easier to understand for me if I draw the borohydride, the BH4-, like this. And I understand that each of these BH bonds can be used as a nucleophile, and so I'll take my arrow and start at one of those bonds. I'll attack the carbonyl just like every other carbonyl addition reaction we've seen. And we get a species that looks like this, O- again, just like before. I'll draw in all 3 lone pairs so I don't forget. And there's the original H, and I've just added a second H here. And we'll put a circle around that one just so we can keep track of them. And now we have this alkoxide, and the second and last step again, just like above, protonation using the mild acid, and that gives us the alcohol. So by using hydride reduction, we can turn an aldehyde into a primary alcohol. By using Grignard addition, we can turn an aldehyde into a secondary alcohol.